I'd like to do 3 problems for you so that maybe it'll make your homework a little easier to do and you'll understand this concept of binary operation better. So the first problem, we have an operation delta on the set of integers z, and a delta b is the absolute value of a minus b. So I say here clearly delta is a binary operation because you can check easily for that. There's 2 things. One, does it work for all a and b in the integers? Can you take the absolute value of any 2? Yes. And you always get one answer. You can't get 2 different things. So this is a well-defined operation, or we say a binary operation. Is it associative? Well, we have to check for that, and you should know what associative means. If it's associative, then a delta b delta c is equal to a delta, in parentheses, b delta c. We're asking, is that true? So take the left-hand side, a delta b delta c. That's equal to the absolute value of a minus b delta c. Just do one at a time. And that's equal to the absolute value of the first number, which is absolute a minus b minus c. The right-hand side, a delta parentheses b delta c, is equal to a delta, and do the parentheses first, so we have absolute b minus c. And that is the absolute value of a minus the absolute value of b minus c. Now, because you have been working with these kinds of expressions for so long, you probably know that this is not true. So you just take like a counter example. Let's I'll do it in a different color. Let's let a equal 1, b equal 2, c equals 3. If it doesn't work, then we're done talking about it, because associativity has to hold for all a, b, and c. So let's see, 1 delta 2 delta 3 is equal to the absolute value of 1 minus 2 delta 3, which is 1 delta 3, which is the absolute value of 1 minus 3, which is equal to 2. Now let's do it the other way. 1 delta 2 delta 3 is equal to 1 delta, the absolute value of 2 minus 3, which is equal to 1 delta 1, and that's the absolute value of 1 minus 1, which is 0. And we see that these two are not equal, and we can conclude then, therefore, the corners of a triangle, put dots there, that means therefore, delta is not associative. It's not an associative operation. Well, what about commutative? Is it true that a delta b is equal to b delta a? If that's true, then the operation is commutative. And in this case, we know that the absolute value of a minus b is the same thing as the absolute value of b minus a. So this implies that delta is commutative. Whoops, C-O-M-M. I'll just abbreviate. It is a commutative operation. So we checked it is a binary operation that is not associative. It is commutative. And now, does it have an inverse? Well, for inverses, an identity. For checking for an identity, we're asking, is there a number, is there an integer, call it e, such that a delta e is equal to a for all a in z, for all a. In other words, the absolute value of a minus e is equal to a for all a in z. Is there such an e? Well, we know that 0 is the only candidate, because certainly the absolute value of 9 minus 0 is 9. But we could say, well, all right, a minus 0, the absolute value, this is a delta 0, is equal to the absolute value of a minus 0 is the absolute value of a, which is a if a was a positive number or equal to 0. But if a is a negative number, a delta 0 is equal to the absolute value of a minus 0, which is the absolute value of a, which is the opposite of a, isn't it? The opposite of a, if a is negative. Excuse me, that's my dog, Oscar. You'll probably hear him in several videos. So there is no identity. There is no identity for this operation delta. And since there is no identity, therefore no inverses. Inverse is defined in terms of an identity, so we don't even ask the question if there's no identity for the operation. Now, the second problem is one where we only have 4 elements in the set S, and we're given the definition of the operations. One operation is star, the other using the @ symbol, by just looking at a table, an operation table. So there's some shortcuts when you're given a table where you can tell if it's commutative or you can spot an identity quickly. We want to check these for being well defined. In other words, are they binary operations on S? And it's easy to look there and see. In each row and each column, you have, in each cell, you have one element of S. And so B star C, for example, is defined, and it is only one thing. So every box is filled with one element of S, so it is a binary operation and well defined. But we want to check for associative and commutative and check for identity, and if there is an identity, then we want to look for inverses. So let me scroll down here, and we'll look at star first. Okay, so first let's check for associativity. Is star associative? So, well, let's look at A. We're asking, is A star, let's just take an example, A star, B star, C. A, B, and C are in S. That will be equal to A star. Now, B star C, you go to the left, B star C is B. And now A star B is C. And then let's look at A star B star C. A star B is C, and C star C is C, C, you get D. Now, there's really 24 different ways I could rearrange these things and check them, but I don't want to go through all that. So I just tried one triple here, and I see that it is not associative. I don't have to try any more because my answer is no. But the associative property is pretty hard to check for given a table because you have so many triples to try. If I had found that these two were equal, it would not mean that the operation was associative. I'd really have to check them all. And I couldn't use like properties of absolute value that we already knew about. But whoops, sorry about that. We're not going to do that because we'll soon be working in algebraic structures called groups, and the operations in the groups are always associative, so we won't have this pain to try to think, do we have to check 24 different triples? Here, though, the answer is clearly no, because these two are not equal. So we just picked two triples and found a counterexample right away. Now for commutativity, there's a neat way to check for it. You want to know if the operation is commutative. So you're asking, well, if I use A and B, those are elements of S, so I'll say, is X star Y equal to Y star X, no matter what values in S we choose for X and Y? Is that true? And what you can do is look at go down the diagonal here, and if you see everything else is symmetric with respect to that diagonal, then you know that the operation is commutative. Because B star D is here, and D star B is here. And look, those are symmetric boxes. So if your table is symmetric across that diagonal that I drew, the operation is commutative. And be sure and check that and see why it's true. We have yes, star is commutative. Now you want to check for an identity, and that's also very easy to check for when you're given the operation table. Because if you're looking for an identity, you want to know, is there an E such that I'll use X star E is equal to E star X is equal to X for all X in S. In other words, if it is, you want to have this column A, B, C, D somewhere in here, because you want A star E to be A, B star E to be B, C star E to be C, etc. So if you find this identical column here, and then this is commutative, so we know if we did, we'd find this row in the right place, then it would have an identity, but this one doesn't, because we don't see that column anywhere. So in this case, we have no, and therefore no inverses. Now let's look at our other one. I'll change color and go back up here, and I should have put these in different rows. Let's look at the operation on S, the set containing A, B, C, and D, and let's see if the at operation is associative. Well, again, there's 24 things to check, so I'm just going to check one, and if it is, I'll say, hey, I think it might be. Let's just check A star B star C, and we get A star B. Okay, A on the left, B on the top, we get C. C star C is equal to C star C is A. Now let's check A star parentheses B star C. That's A star. Now B star C is D, and A star D is A. So these are equal, and that does not tell us that the operation is associative, but we think it may be. Let's just say star is likely to be associative, just because that one kind of randomly picked example turned out to be. But on a test, I'm not going to ask you to prove that an operation is associative if you have to go through all that. I would ask you one like in the first problem where we were dealing with absolute value and differences, two things that we already knew how to work with algebraically. In one like this, I would just tell you it's associative. Okay? Now for commutative, is at commutative? Well, we'll look up across that diagonal again, and you see C, C, B, B, D, D, A, A, B. Yes, because we have that symmetry across the diagonal. And how about an inverse? Well, we want how about an identity? We want to know, is there a number such that A at E will be A, B at E will be B, and we look over here and see here is the same column, A, B, C, D. A, B, C, D. So A star D is A, B star D is B, C star D is C, and D star D is D. So we have an identity. The identity is D. And notice, we already know it's commutative, so we don't really have to check this, but notice that we have that row, this row on the top appearing down here. So we have the identity working on both sides of every element. So here we need to ask about inverses. Here I'm going to do this up at the top. Excuse me. Okay, so I'm going to do inverses up here. I think I'll change color. Okay, so now what is, we have an identity, so let's see, do we have an inverse for A? A star something equals D. Well, yes, A star A. So A is its own inverse because A star A is equal to D, the identity. B inverse is equal to, well, B, excuse me, not star, I'm sorry, it's the at. B inverse is equal to C because B at C is equal to D. And likewise, C inverse will be equal to B because we have the commutative property. Or you could look here, C at B is equal to D, the identity. And now D inverse is equal to itself because D at D is equal to D. The identity is always its own inverse. Okay, so we had inverses there, and that answered all of the questions for number 2. Problem 3 is defining a binary operation delta using the least common multiple, which you have had probably in a couple previous courses. Is it well defined? Well, yes. Given any two natural numbers, there's always a least common multiple, and there's only one of them. Just to review, let's just calculate 6 delta 8, for example. That is equal to the least common multiple of 6 and 8, the smallest number that's a multiple of them both. Well, I always like to factor them. This is 2 times 3, and this is 2 times 4. So my least common multiple is going to have to, of course, be a multiple of 6, and it'll need that factor of 4. So we have the least common multiple of 6 and 8 is 24. The smallest number that's a multiple of them both. Now, something you might want to remember about least common multiple is the least common multiple of 3 things, like 6 and 8 and 10. Well, you can take the least common multiple of 6 and 8 and then consider the 10 or in any order you want. You still would just look at the prime factors here. You have 2 times 3. This has a 2 and there's times 4, and this has a 2 and 5. So our least common multiple will certainly be a multiple of 6, and it's going to need those 2 extra factors of 2 to be a multiple of 8, and it's going to need the 5 to be a multiple of 10. So the least common multiple will be 120. Now, it doesn't matter if you can do them all at once like I did, or you could find the least common multiple of 6 and 8 and then do it with 10, or 8 and 10 and then take that common multiple of that with 6. Hopefully you you had this in number theory and it'll come back to you soon. Alright, so now let's answer the questions. Certainly it's well defined. Is it commutative? Well, of course. M delta n is the least common multiple of m and n, which is the least common multiple of n and m, makes no difference what order you put them, which is n delta m. So we have, yes, it's commutative. For associativity, it's definitely associative, yes, because m delta n, in parentheses, delta k, let's say, is equal to the least common multiple of m n delta k. Now I could keep writing, it's going to look weird when I write it all out. This would be the least common multiple of the least common multiple of m and n, comma k. All this is saying is that if I find the smallest number that's a multiple of the first two, find that number, and then find the smallest number that's a multiple of that and k, it's the same thing as I did up here. It's just the same as, let me write that, and you don't need to prove this, it's just the same thing as taking the least common multiple of m, n, and k. It doesn't matter what order you do it in as far as parentheses. So, well, I'll say, and this is equal to then m delta n delta k. And we have an associative operation. So it's commutative and associative, well defined, and we want to know, is there an identity? And if so, what elements are, notice the word invertible, meaning which ones have inverses. That's a word that you should get used to seeing. You could see that on, on a test or in homework. Invertible just means the element has an inverse. So to answer the question, is there an identity, we will ask the question then, is there a number, let's call it E right now, E, a natural number E, such that A delta E is equal to E delta A is equal to A. Well, it's commutative, so really we're just asking, is there a number that gives us back the number we started with? Well, yes, because the least common multiple of some number A and 1 is always A. So 1 is the identity. 1 is the identity for this operation defined as delta. So now we do ask the question, what about inverses? For which numbers n is there a number m such that n delta m equals 1? In other words, the LCM of n and m is equal to 1. The least common multiple is equal to 1. Well, there are no numbers like that except for 1. So, and we know 1 is the identity, and it's always its own inverse. The least common multiple of 1 and 1 is equal to 1. But if you put in any other numbers other than both 1s, you're not going to get a common multiple of being 1. So we say that 1 is the only natural number with an inverse. 1 inverse is equal to 1.